Hello and welcome to Lecture 10 for the course ECE 257A, Fault-Tolerant Computing. This lecture deals with the concept of error correction, in particular error correcting code, and their use in one of their most important uses in building disk arrays to store lots of data without the risk of losing data. So this will be chapters 14 and 16 in my textbook on dependable computing. So we start as we did for error detection by looking at the code we already know, although we didn't talk of it in terms of coding. Triplication allows us to correct an error in any single computation channel out of the 3 channels. So basically, when we triplicate a unit and use a voter to vote on the 3 computed results, we are essentially using a triplication code where X is encoded as 3 copies of X. So X is represented as XXX. This is 200% redundancy. Then we compute separately on each of those copies of X and then vote. The majority of these results will determine what the output will be. So if one of these results is corrupted, is incorrect, the 2 correct one will determine what the output should be. So encoding is trivial, basically copy X 3 times. Decoding consists of this voting process. And redundancy, as I mentioned, is 200%. Now, if we also triplicate the voting unit so that we have 3 voters independently voting on these 3 outputs, then we basically start with coded inputs. We can start with coded input, 3 copies of X, and obtain a coded output, 3 copies of Y. It's still tolerant of single faults, but it allows us to compute directly encoded values. In other words, we don't need encoding and we don't need decoding. Now, with a larger replication factor, so for example 5 copies, more errors can be corrected, but it very quickly becomes expensive. Even triplication is rather expensive. Despite the fact that hardware nowadays is very cheap, triplication is still not the most desirable way of achieving error tolerance. So our challenge in this chapter and in this discussion is to come up with strong correction capabilities using much lower redundancy, perhaps an order of magnitude less. So instead of 200% redundancy, maybe we have 20% or 30% around that ballpark. So we want to have much less redundancy while still having pretty strong error correction capability. Okay, now to correct all single-bit errors in an n-bit code, we must have r redundant bits so that 2 to the r is greater than n. This is easily proven. And therefore, we need about log 2k, at least log 2k check bits for k data bits. Okay, so the amount of redundancy is logarithmic, at least, in the number of data bits. So this is a lower bound. Okay, some codes have more redundancy, but we need at least a logarithmic number of bits for k data bits, redundant bits for k data bits. So this is similar to the diagram I showed you for error detecting code. We have data words, and those data words are encoded as code words within the code space. And some words in this code space are code words, valid words. Some are non-code words, invalid words. And this is basically what allows us to correct errors. So if a code word changes to a non-code word, and if this relationship is sort of is not one to many, in other words, it's not many to one, so that multiple code words are not mapped to the same non-code word as a result of error, then we can go back and correct the error. And in this example, you see that no matter which of these red points we get, it's associated with only one green point. Therefore, we can go back and correct the error. If we happen to have, for example, an arrow from this green point to this red point, in other words, this code word could change as a result of an error to this non-code word, then we would be in trouble because we cannot go back and correct the error. Because if we receive this erroneous word, we are not sure whether the correct word was this one or this one. As long as we don't have many to one mapping, then we'll be able to correct the error. So here is a conceptually simple error correcting code. It's not particularly efficient, but it's very easy to understand. So let's get started with this one. So we have k data bits. We arrange them into a square root of k by square root of k square array. Okay? So for example, these blue bits, 9 bits, are data bits. And I've arranged them into a 3 by 3 array. And then the redundant bits, which are the green ones, are parity bits for rows, parity bits for columns, and this one parity bit at the corner, which can be viewed as parity bit on this column or parity bit on this row. Okay, so for example, the first row, the top row, is 0, 1, 1. It has 2 ones. So if we assume even parity, the parity bit will be 0. The next row has a single 1, so its parity bit for even parity will be 1. 1, 1 will be 0. Similarly, in this column, 1, 1, so the parity bit is 1. 2 ones, parity bit is 0. And 2 ones, parity bit is 0. And then it's easy to prove that this corner bit doesn't matter whether you use the parity of this row or the parity of this column, you get the same thing. So now in this 4 by 4 array of bits, any single bit can change and you can correct it. Let's see why. Let's say this 1 over here changes to 0. What happens? Then parity check is violated for this row. This row no longer has even parity. Parity check will be violated for this column. The intersection of the row and column for which the parity check is violated pinpoints the location of the error. And you can go and change that bit to make it correct. Okay, let's see what happens if you have 2 erroneous bits, like these 2 bits highlighted in purple. If these 2 bits are in error, let's say this one changes to 0 and this 0 changes to 1, then parity bit for this row will not be violated. But parity bit for these 2 columns will be violated. So you will know that something is wrong, but you don't know what is wrong. You know something is wrong in this column because the parity check was violated. And something is wrong in this column because all the row parities are okay. Okay, you don't know the double error, which row contains the double error. Okay. Of course, if the two errors are not in the same row or in the same column, the situation will be different. So for example, let's say this bit and this bit, these two bits change. Then you will have two row parity violations and two column parity violations. And then you don't know which of these 4 bits is in error. Okay, so double errors are detected, but they are not correctable. Single errors are correctable. What about triple errors? Well, if you think a little bit, you will see that the worst case pattern of triple errors are these 3 that I've shown here. If these 3 ones change to zeros, then parity bit for this row will not be violated because there are 2 changes. For this column will not be violated. But for this column and this row, parities will be violated. So that triple error will be mistaken for a single error in this position. So in other words, you may go and try to correct this bit, which is not in error, because you would think that the parity for this column having been violated and parity for this row, this is a single error that is in this location. So triple errors, some triple errors are indistinguishable from single errors, and therefore you cannot detect them. Okay, because you may go and try erroneously to correct another bit that is not in error. So this is basically a single error correcting, double error detecting code. Okay, its redundancy, at least in this example, is rather high. You have 9 data bits, and 7 redundant bits. So 7/9, which is about 80%, is the redundancy. Of course, as the number of data bits grows, so if you have, for example, a 10 by 10 array of data, 100 bits, then you will have 21, so 21 redundant bits for 100 data bits, that's 21%. So redundancy shrinks as the size of the data increases, but the capability is still the same. It's single error correcting, double error detecting. Okay, error correcting codes are evaluated pretty much the same way as error detecting codes. We think about redundancy, how much redundancy they involve. The greater the error correction capability, the higher the needed redundancy. So we try to keep the redundancy low, as low as we can. Encoding and decoding complexity in terms of circuits and in terms of time needed to encode and decode. The capabilities of the code, basically what types of errors does it correct for us? Single, double, byte, b-bit burst, unidirectional, and so on. And then we sometimes provide, as we saw in the example on the previous slide, combined error correction and detection capability. This makes the system safer because up to a certain number of errors we can correct them. If the number of errors exceeds that level, the correction capability, then we at least detect them and the system remains safe. So to correct C errors and additionally detect D errors, where D is always greater than C, a minimum code distance of C plus D plus 1 is required. For example, Hamming single error correcting, double error detecting code. So C is 1, D is 2, has a code distance of 4. Okay, Hamming distance for error correction should be at least, a single bit error correction requires a Hamming distance of 3. And this diagram shows this graphically. These red circles are code words. The yellow circles are words that are distance 1 away from the code words. And you see distance 1 code words from this one are distinct from distance 1 from this code word, and distinct from distance 1. So you can tell, if you get this erroneous value, you can tell that it came from this. You can go back to this and correct it. But distance 2 in this example, 1, 2, 1, 2, 1, 2, there's a shared point, the shared data word, that is distance 2 from all three of these. So if you happen to get this incorrect data word, you won't know, what is the correct value. So you have just detection for that one, not correction capability. Okay, perhaps the most famous error-correcting codes are Hamming codes. So this is an example, the smallest Hamming code, which has 4 data bits, D3, D2, D1, D0, 4 data bits, and 3 parity bits, P2, P1, P0. And the parity bits are defined and a subset of the data bits. So parity bit 0 is based on D0, D1, and D2. In other words, you XOR together those 3 data bits, and that gives you this parity bit. P1 is the XOR of D0, D1, and D3. P2 is the XOR of D1, D2, and D3. So each of the parity bits corresponds to a subset of the 4 data bits. The reason they've been selected in this way is that they allow then error correction. So forming the parity bits, in other words, encoding, requires 3 XOR networks. Okay, you have to do 3-bit XORs to compute each of these. That's encoding. Checking the correctness of this code word requires 3 XOR networks, each of them doing 4-bit parity computations. So P0, D0, D1, and D2 are XORed together, and if the result is 0, then we know that that part is okay. Okay, so you need 3 XOR networks to verify parities. Decoding is trivial because this is a separable code. The data part is separate from the check part. Therefore, you just look at these 4 bits. There's no decoding involved. Redundancy for this example is 3 check bits for 4 data bits. So it is 75% redundancy. 3 for 4, 75. So it's quite high. However, as the number of data bits increases, excuse me, as the number of data bits increases, the redundancy factor gets better. So for example, if you have 26 data bits, you need only 5 check bits. So 5 for 26, that's a little bit less than 20%. If you go to 120 data bits, you need only 7 redundant bits. So that's 7 divided by 120, roughly 6%. So redundancy improves as the code gets larger. Now, in order to, once you receive a data word like this, a 7-bit data word, and you're trying to find out if anything is wrong with it, whether it contains an error that needs to be corrected, you form what are known as syndromes. The syndrome has 3 bits in this example. That's basically the 3 parity checks. So you expect all of these syndrome bits to be zeros because all these parity checks need to be correct. So 0, 0, 0 means that there's no error in this code word. Of course, remember that we are doing single bit error correction. If you have double bit errors or triple bit errors, then you won't be able to do anything. You may not even detect that. Okay, so for example, if this syndrome is 1, in other words, this parity check fails, so you have P2 equal to 1, P1 equal to 0, P0 equal to 0. Sorry, sorry, S2 equal to 1, S1 equal to 0, S0 equal to 0. So 1, 0, 0 is the syndrome, and 1, 0, 0 being the syndrome means P2 is the erroneous bit, and you can go and correct. Why is that? Because if this parity check fails, means some bit in this equation, in this expression, is in error. Now D3 cannot be in error because D3 also appears here. So if it were in error, this one should have failed as well. D2 cannot be in error because D2 also appears here. D1 cannot be in error because it also appears here. Okay, P1 cannot be in error because this parity check did not fail. And P0 cannot be in error because this parity check did not. So that syndrome 100 pinpoints P2 as the erroneous bit. And each distinct syndrome, 000 of course is no error. Each of the other 7 patterns in the syndrome pinpoint one of the 7 bits as being in error, and therefore you can simply flip that bit and correct the error, assuming that the error is single. There's just one bit error. Okay, so Hamming single error correcting code can be formulated in terms of matrices, and this is helpful to see the patterns and extend the code to larger codes. So this is the same code. We sometimes call this the 4-7 code, meaning there are 4 data bits and 7 total bits, the 4-7 code. So this is the notation used for error code. KN code means K data bit, N total bits. So there's a matrix called the parity check matrix, which when multiplied by the received word generates the syndromes. This basically says, now one point I should make here is that when we talk about matrix multiplication or matrix by vector multiplication in the context of binary error code, so normal matrix multiplication would use multiplication, say 1 times D3, then plus 1 times D2, so you need multiply and add, arithmetic operation. In the context of error codes, binary error codes, we do AND, so 1 and D3, which is the same thing as multiplication, so that part is not different. But when we do then exclusive OR, so 1 times D3, XOR 1 times D2, XOR 1 times D1, and so on. So that's basically the parity check, because we are doing D3, D2, D1, and P2. D3, D2, D1, and P2, this is this parity check, and it generates S2. Okay, so we construct a parity check matrix that when multiplied by the word, the suspicious word, gives you the syndrome, as I mentioned before. If the syndrome is 000, everything checks out, and the data word is correct, and then you can use these 4 bits. If it doesn't check out, if one of the syndrome bits is equal to 1, then you consult this table to see which of the data or parity bits is in error, and then you can go ahead and correct that. Notice that the bit that is in error, the columns of this matrix, if you read them as binary numbers, so you have here 110 is 6. So if the syndrome is 6 as a binary number, D3 is in error. 6 is D3. If it's 101, which is 5, D2 is in error. Okay, so the syndrome, the column of that matrix that matches the syndrome pinpoints the erroneous bit. Remember, again, I repeat this, that matrix vector multiplication is done with AND XOR rather than the standard matrix multiplication that we are used to, multiply and add. So, as I said, AND is the same as multiply, so you can say it's multiply and then modulo 2 add. Okay, we can rearrange the columns of the matrix, okay? If I, for example, switch the locations of these two columns and also switch the location of these two entries, then the result will be the same. Okay, it doesn't change. So one convenient rearrangement is to rearrange this matrix so that its columns are binary number in order from smallest to largest. 1, 2, 3, 4, 5, 6, 7. So this is a rearrangement of the original parity check matrix. And so the rearrangement is shown here. I should rearrange these bits also accordingly. P0, P1, D0, P2, D2, D3, D1. It still gives me the same syndromes. Now the nice thing about this is that the syndrome directly corresponds to column number. So syndrome 001 says that bit in column 1, the bit corresponding to column 1, is in error, which is P0. Syndrome 100 indicates that the error is in the column 4. 100, column 4, P2s. And this gives me a very simple way for error correction. Okay, so if I take the syndrome, a 3-bit number, and decode it, when I decode it, I have 8 outputs numbered 0 through 7. So if I have 000, output 0 will be asserted. If I have 001, output 1 will be asserted. So if output 0 is asserted, that means everything is okay. So that output of the decoder tells me that everything is okay, if it's 1. If any other column is 1, that points to the bit that is in error. So I simply XOR the remaining 7 bits with the 7 bits arranged in this order. And that gives me the corrected word. Because the only one of the outputs is equal to 1 in the decoder, and that one causes the appropriate bit to be inverted. 1 XOR something is the inverse of that. So that bit is flipped, the other bits are not changed, and I have the corrected. So this is a very simple error correcting circuit. It's just a decoder. You decode the syndrome, and then one bit of the decoder, one output of the decoder, if it's 1, tells you that everything is okay. If any other output is equal to 1, it automatically causes the correction of the appropriate bit. So this is nice. So just in case you're curious, this is Richard W. Hamming, inventor of Hamming code. He was at Bell Labs for many years, and then later in life he went to Naval Postgraduate School up in Monterey, California. A second matrix formulation of Hamming codes is basically a generator matrix. A generator matrix multiplied by a data word gives you the encoded word. If you know this generator matrix has the identity matrix up here. That's because the first 4 bits of the code we want to be the data bits. So 1 times D3 plus 0 times the other one gives you D3. This one gives you D2. This one gives you D1, D0. And this part is basically the parity. So for example, P2 is D3 XOR D2 XOR D1. P1 is D3 XOR D1 XOR D0. This is a second way of formulating Hamming code in terms of matrices. This is called the generator matrix. So this can be easily generalized now to wider Hamming single error correcting code. So the parity check matrix has columns that are 1, 2, 3 in binary, up to 2 to the r minus 1, or redundant bits. These are the data and parity bits. So there are k data bits and r parity bits. And these are the r syndromes. Okay, as I mentioned, the redundancy improves when you have 4 data words, you need 3 redundant bits. When you get up here to 502 data words, you need only 9 redundant bits. And log base 2 of 502 is roughly 9. It's a little bit less than 9. So you roughly need, for large values of k, log 2k redundant bits. Oops. And I mentioned at the beginning of our discussion that that's the minimum amount of redundancy that can allow you to correct a single error. Therefore, Hamming codes are very efficient. And then the correction circuit is basically the same thing. The syndrome is decoded. One output of the decoder tells you that everything is okay. The other outputs are XORed with data and parity bits to correct possible error. Now you can turn any single error correcting Hamming code into single error correcting double error detecting code by adding a row and a column to the parity check matrix and an extra redundant bit. So basically, the ART syndrome is XOR of everything, all the data and parity bits. Okay, and then this, sorry. I'll let it up to you to sort of verify that that is correct. If you take this syndrome and input it to the decoder, so this is sort of like an enable signal. So if this syndrome is 0, this bit will be 0, and then the outputs, all the outputs here will be 0, and therefore everything is okay, and because you're doing parity check on all the bits, any single bit error would make this bit equal to 0. Will violate this parity check. So if this bit is 0, then all the outputs will be 0. If this bit is 1, then the decoder is enabled. Then now if the syndrome is equal to 1, if the syndrome is equal to 0, all zeros, then this bit will be asserted. And that means that we don't have a single error. Okay, there is an error, but it's not a single error. It's a double error. Otherwise, if any other output of the decoder is asserted, then there is a single error, and we just correct that single error. Okay, so any Hamming code can be converted to double error detection capability can be added to it by simply adding one redundant bit, one extra bit. Now, linear codes, of which Hamming code is a special case, are defined in terms of either the generator matrix. So you have the generator matrix multiplied by the data vector gives you the code word, or in terms of its parity check matrix. Parity check matrix multiplied by a word that is suspicious gives you the syndrome. And if the syndrome is all zeros, then all the parity checks are satisfied, there's no error. If the syndrome is non-zero, it uniquely points to which bit or bits are in error. Okay, now this section I'm gonna skip pretty much. I put it there so that you have heard of these other codes. BCH, Bose Chaudhary Hockengham code, BCH, of which special case Reed-Solomon codes are very popular. So Reed-Solomon codes are special cases of BCH code. Here's an example of Reed-Solomon code. The popular variant is Reed-Solomon 223 bytes of data. So this is not binary. It's the symbols in this code are bytes. 223 bytes of data and 255 minus 32 redundant bytes of data. And this can correct errors in up to 16 bytes anywhere in the code. This is a very strong correction capability. Any 16 bytes, they don't have to be consecutive, in other words, not just burst errors, anywhere. Any 16 bytes that are erroneous can be corrected. And this is used in CD players, or was used when CD players were still being used, digital audio tape, and in digital television. So 223 bytes, you have to multiply it by 8. So that's about 1800 bits. It's a big block of data. Now in these CD players and digital television, you deal with big blocks of data that are transmitted. And then you add 32 redundant bytes to it, and it becomes highly resilient. It can correct up to 16 bytes. Okay, this is all I want to say. If you are interested, as I mentioned last time when we talked about error detecting code, coding theory is a really broad topic. There are many different codes, many different theories for those codes, and each code finds basically some applications in view of its strengths in correcting or detecting the types of errors that we are interested in. So there are many, many codes. So I'm going to skip these a little bit more detailed discussion of Reed-Solomon codes in terms of Galois fields, and then move to arithmetic error correcting codes. Last time I discussed arithmetic error detecting codes, in particular product codes and residue codes. Now residue codes can be easily extended to correct errors in the following way. So suppose you have 12 bits of data, okay? Remember, when we talk about single arithmetic error, we means the addition of a power of 2 or the subtraction of a power of 2. So single arithmetic errors for these 12 bits of data can add 1 to the 0 to the 1 to the 2 all the way to the power 11, or can subtract to the 0 to the 1 up to the 11 from the code word. Okay? Now if we use for these 12 bits of data 2 modular check, modulo 7 residue and modulo 15 residue, then an error that is 1 in magnitude adds 1 to the modulo 7 and 1 to the modulo 15. In other words, these residues normally have to be, the data word has a particular residue here. If you increase the data word by 1, its mod 7 residue will increase by 1. Its mod 15 residue will increase by 1. Okay, if you add 16, the mod 7 residue will increase by 2 because 16 is 2 mod 7. And the mod 15 residue will increase by 1. And similarly for the subtraction. Now, if you compute the syndrome of a particular word, and you see that the mod 7 residue is off by 6, and the mod 15 residue is off by 11, syndrome 611 pinpoints the error. The error is negative, and it's 2 to the 6. In other words, 2 to the 6 pinpoints a particular bit in the data word that is in error. Notice that all these syndromes are unique. That's why we can correct a single error. In other words, 611 does not appear anywhere else. Okay, 67 only appears here and nowhere else. So because these syndromes are unique, they pinpoint the location of the error that we can correct and will be done with. Now, why do we have only 12 data bits? What happens if I have 13 data bits with the same modular checks? It turns out that the 13 data bits, if it flips from 0 to 1, this is the error magnitude. The 13th bit is 2 to the 12. This is 2 to the 12, which has residues of 1 and 1 with respect to 7 and 15. And then this syndrome will be indistinguishable from this syndrome. So the maximum number of data bits that you can have, and for these syndromes to be unique, is 12. Because starting at bit 13, the syndromes start repeating, and therefore you cannot uniquely pinpoint the error. Now, generally speaking, this is an instance of bi-residue code. Bi-residue means you have two residues. And both of the residue moduli are of the form 2 to the a minus 1. This is 2 to the 3 minus 1. This is 2 to the 4 minus 1. And generally, if you use two residues, 2 to the a minus 1 and 2 to the b minus 1, which are relatively prime, which was the case for 7 and 15, it supports a times b bits of data for weight 1 error correction. So a was 3 in the previous example, b was 4. 3 times 4 is 12. Okay, so if you want to have more than 12 data bits, then you have to use different a and b, lowercase a and b or uppercase a and b. So for example, if you choose lowercase a and b 5 and 6, which means 31 and 63, which are relatively prime, 31 and 63, then you can have up to 30 data bits. If you choose 11 and 12, so there's 2 to the 11 minus 1, which is 2047, and 2 to the 12 minus 1, which is 4095. With those two check moduli, you can have up to 120 data bits. So redundancy, as is the case for almost all codes, redundancy improves. Here you had 7 redundant bits for 12 data bits. That's about 60%. Here you have 23 data bits, 23 redundant bits for 120. Okay, this is 20-some%, so it gets lower and lower. Comparing with Hamming, of course, redundancy is pretty high. So for example, take this 120. Here you have 23 bits of redundancy. Hamming weight with 120 data bits for single error correction requires only 7 redundant bits. So redundancy is lower, but this is the price we pay to be able to keep the code closed under arithmetic operations. So you can add, multiply, subtract without having to remove redundant bits from the code. So that provides some protection during the arithmetic operations. Okay, this one basically says you need 2 check processors. So if you have modulo 7 and modulo 15, so each input has 2 things attached to it, the residues. And then those 2 things, each of them goes into a separate check processor. And if both of those residues that you compute match the residues of mod A and mod B of the result, then you are okay. Otherwise, you have an error. Okay, so here is just a listing of other codes that you may have heard about, but as I mentioned, I just wanted you to have a picture of what error correcting codes are about and see some examples of such codes. And any other codes that you need to study, now you have the basics, you have the foundations to go and study those codes. So these are some of these codes: Reed-Muller codes, turbo codes, low density parity check codes. These are pretty popular nowadays. And the information dispersal, which basically encodes data into n pieces such that any k of the pieces are adequate for reconstructing the data, is a form of error coding. So you basically tolerate up to n minus k erasures in this case. So you have n pieces of data, any k of which are adequate to reconstruct the original data. So if n minus k pieces disappear or erased, you still will be able to construct the data. So this is a kind of erasure code. Okay, these discussions I'm going to skip because we're going to come back to this, in particular algorithm-based error tolerance later. This is just a preview that I'm going to skip so that I have time to go into chapter 16 and discuss redundant disk arrays, which is a very important application nowadays of error correcting codes. So first, a brief overview or review, I should say, of disk memories. This is a typical disk memory, magnetic disk memory, with multiple platters, 4 platters. Each platter typically has 2 recording surfaces, one on each side. And then they are assembled on this spindle, and they rotate at very high speed. Say 2700 RPM, 2700 revolutions per minute is common for disks today. The read-write heads are attached to these arms, and all the arms are attached to an actuator. And this actuator basically rotates around its axis. As it rotates, the heads move outward or inward on the disk, aligning themselves for the different tracks on which information is stored. So this top arm has just one head. The second arm may have 2 heads, one reading the bottom of this platter and the other one reading the top of the next platter. So these move together. So in other words, if this head is on the first track of this platter, of this surface, then this one will also be on the first. In order to read data, you move the actuator so that the head is aligned with the track that contains the data to be read. And that's because it's a mechanical motion. It takes a relatively long time compared with computer speed. It takes many milliseconds, whereas in digital circuits, we talk about nanoseconds or fraction of nanoseconds to do operations. So disk memory is extremely slow compared to electronic circuit speeds. So there are tracks, and each track is divided into sectors. A sector is basically usually the unit of data transfer from disk. So we go to a disk to read a sector, and that sector happens to be on a particular track. Okay, so these are some modern disks I just looked up on a website. So this is up to date, although the web page says 2016. The web page, the URL says 2016. The data is actually 2020. So they updated the web page without changing the name of the web page. So these are typical modern disks. Seagate is one of the important manufacturers. 4 of its products are featured here. Western Digital is another one. Okay, and 3 of its products are featured here. So these are names of disk drives. Prices of these disk drives are mostly, with a few exceptions, that are under $100. So disks are very cheap nowadays. Capacity is in the range of 1 to 20 terabytes, again with a couple of exceptions. So it's multi-terabytes. Each of them comes with a cache memory with a capacity in the range 64 to 256 megabytes. Now cache memory, because the disk is slow, helps in the following way. If you read a file from the disk and then you make modifications on the different parts of the file and then store back the file, you read the disk only once and bring the file, provided the file is small enough to fit in this cache memory. You just read once and then write once. So you minimize the number of disk accesses. The cache memory is solid state memory, is SRAM or DRAM, and therefore it's pretty fast to access. The data rate of these disks are on the order of 6 gigabits per second. So it can transfer the data at a very high rate. Okay, so this is just to give you an idea. Now, this low price is important because we are going to be talking about RAID, redundant arrays of independent disks. Initially, this acronym stood for redundant arrays of inexpensive disks. Now, we no longer have expensive disks. Hard disk drives are very inexpensive, and therefore they changed that I to stand for independent rather than inexpensive, because there's no such thing as expensive disks. And I'll tell you why there are no expensive disks. So this is basically a schematic of what happens when you try to access a sector on the disk. There are 3 phases to the access. One is called the seek time. The head must move from wherever it happens to be. Usually the rest position for the head is outside the disk. If it's in the rest position, it has to move here. If it's here and now you access something else, let's say on this track, then it moves from its current position to this position. So that's called the seek time. As I mentioned, it's on the order of milliseconds. And it's a function of how many tracks you move. If you move C tracks, the seek time is a function of C. Now, if this movement were uniform, the constant speed, then this would be a linear function. But because it involves acceleration of the head at the beginning and then deceleration at the end, it also has this square root term. So it's a function of C. The more you move, the higher the seek time. Then once you get to the track that contains the data may be somewhere else on the track. You have to wait for the disk to rotate and for data to come under the head. And on average, you wait half a disk rotation. In other words, if you're very lucky, the data happens to be here. As soon as the head arrives here, it starts reading because the data is right there. If you're very unlucky, the data just passed under this point and it's here, you have to wait a full rotation to get the data. So on average, half a rotation is needed. And that half a rotation is obtained from this formula. 30,000 divided by the RPM for the disk. So if the RPM is 3,000, this will be 10 milliseconds. Okay? Then finally, once the data arrives under the head, it takes a while to read all the bits in that sector. This time is negligible. Okay? You can basically ignore it without committing much error. Because the sector is such a small fraction of a track, the reading part is very small. Typically much less than 1 millisecond. Whereas this could be 10-15 milliseconds. This rotational latency can be 10-15 milliseconds. So that's negligible. Okay, now this one I'm going to skip so that I can finish within a reasonable time. Now, in the early days of supercomputers and high-performance computing, we had all these expensive, fancy disks that people built in order to try to match the performance of the disk to the performance of the CPU. So as I mentioned, the disk is much slower than the CPU, and therefore these seek time, rotational latency are really huge. The CPU would be sitting and waiting for a long time for data to come in from the disk. So they tried to modify the disk. One modification was to provide one head per track. These were known as head per track disks, instead of just a single head that moves back and forth between the tracks. So this eliminates the seek time because the head is permanently on the track and you just select the head that needs to read. And that selection is electronic, and therefore it takes very little time. But these disks are very expensive because you have to build a large number of heads, and building these heads and making sure they're aligned with the tracks is non-trivial. In some cases, they went further and said, okay, let's provide two sets of these heads so that the average rotational latency can be 1/4 of a rotation rather than 1/2. Okay, so for example, if the data is closer to these heads, if it happens to be here, you read them with those heads. If the data happens to be closer to this one as the disk rotates. So in this way, you eliminate the seek time altogether, and you reduce rotational latency by 1/2. If you actually provide 4 sets of head, then you reduce it even further. Okay, however, these expensive disks, such as this one, had a very limited market. You know, how many supercomputers are there in the world? You build these disks in thousands of units, whereas disks for personal computers, laptops, and so on, you build them in tens or hundreds of million units. So the economy of scale will lead to reduction in the cost of those disks. They're much cheaper. And therefore, these disks are no longer cost effective. So people started to think, okay, how can we use those cheap disks, which are of course smaller than these disks, and also perhaps less reliable because they're mass produced, to build disk memory units for supercomputers that are very large and also very reliable. Okay, so the idea is that use these small disks, inexpensive disks, many of them, to provide high capacity, and also use redundancy to provide high reliability. Okay, so these disks basically vanished. We no longer build these specialized disks. what we try to do is use the same kind of disk that is used in a laptop or personal computer, but assemble them into disk arrays that provide high capacity and high reliability. Okay. So the ideas of mirroring and striping are discussed here. These were basically early ideas along this line. So to make these inexpensive, mass-produced disks more reliable, one idea is mirroring. Any data that is stored on this disk is also stored on a mirror disk. So you're basically duplicating the data. This is sort of a parallel system. In other words, as long as one of these two disks operates correctly, you have access to your data. Okay, remember that disk memories have very strong error correcting codes for storing data on the disk surface. Therefore, it's very unlikely for the data to become corrupted and for you not to detect that corruption, because those codes are very strong. They either correct the corrupted data or at least signal that something. So if you're using this disk and you notice that data is corrupted, you switch to this disk, which has a copy of every piece of data on this disk, and use that. So this is basically a parallel system. Therefore, it will have extremely long life. It is highly reliable. So that's the idea of disk mirroring. Now, disk striping is used to increase the throughput, data throughput from the disk. So if you have a file that you want to store, instead of storing the entire file on one disk drive, divide it into pieces, segments, and then store each segment on one of these disks. This allows you to access the data at 4 times the throughput of a single disk. In other words, you can access 4 pieces of data at once, therefore the throughput increases. Unfortunately, this is a series system. In other words, if you lose one of these disks, which contain a part of data from every file, then all the files basically become corrupt, and you can't reconstruct the data. So this is a series system. It increases the throughput, but it decreases the reliability substantially. Okay. So the next idea, and I'm going to go through a sequence of ideas rather quickly for different types of RAID system, was to use coding. And coding can be applied to bits. So for example, you can take 1 bit from this disk, 1 bit from this disk, 1 from this, 1 from this, compute a parity bit, and store it on a 5th disk. Now, if this disk fails, so that you lose access to this 1 bit, so the parity bit is basically the XOR of those 4 bits. Okay, so if you lose, let's say, the bit D, this disk crashes and you lose access to D, D can be constructed by XORing the example given here is in terms of B. If B is corrupted and therefore you don't have access to this bit B, B is the XOR of A, C, D, and P. This is the property of parity computation. Okay, you can also do these XOR on blocks of data rather than bits of data. Doesn't matter. So you take this block, XOR it with this block, and so on. That will be the parity block. And then if you lose access to this block, you reconstruct that block by XORing the 4 blocks A, C, D, and P. So this is the redundancy, the simplest kind of redundancy that you can think of in a RAID system. Okay, so here is basically a snapshot of all the different RAIDs that have been defined over the years. From RAID 0, which is basically just mirroring multiple disks for, RAID 0 is striping. It has no redundancy, just higher data rate. RAID 1 is mirror disk. It improves the reliability, but it has a very high redundancy. you have double, you need double the storage space. RAID 2 used error correcting codes, but quickly they came to the conclusion that this is really not an efficient way of doing things. RAID 3 uses bit or byte level striping. So you have these, let's say, bytes on the 4 disk, and there's the parity byte on the parity disk, and then there's a spare disk, so that if this disk crashes, you reconstruct the data of that disk on the spare disk, and then you can continue operation as if nothing happened. Unfortunately, however, and we'll talk about this a little bit more in a minute, this is very time consuming. You know, disks these days are huge. So if you want to reconstruct the data on this disk, many hundreds of megabytes or even terabytes, each byte to be reconstructed requires 4 disk accesses. This one, this one, this one, and this one. So it takes hours and sometimes days to reconstruct the data on the spare disk. And meanwhile, during this long period of time, there's a chance that the second disk fails, and therefore you actually lose data because you are not set up to tolerate more than one disk failure, and you don't even have more than one spare disk. Okay, one of the disadvantages of this RAID 3 is that this parity disk quickly becomes a bottleneck. As long as you are reading data, you're fine. You read this piece of data, or you read this piece of data, no problem. But if you want to write something onto this disk, you want to write into this byte or this block, writing to that block also modifies the parity, changes the parity. So anytime you write in any of these disks, you also have to write a new parity block on the parity disk. So this parity disk becomes a bottleneck because you have a lot of accesses to this. Basically, you add up. If you have 10 write accesses to each of these 4 disks, then you will have 40 accesses to the parity disk to modify the parity block. So RAID 4 basically removed this bottleneck. RAID 5. RAID 5 removed this bottleneck, but distributing the parities by not putting all the parities on one disk, but distributing the parities. So these 4 blocks have their parities stored here. These 4 blocks, the white ones, have their parities stored here. So parity accesses are also distributed among the disks. Finally, RAID 6 provides a second checking mechanism to allow double disk failures. I mentioned up here that reconstructing the contents of one of these disks takes a long time, and it's possible that a second disk failure occurs before you have completed the reconstruction, and therefore you lose data, and that's undesirable. So RAID 6, the most recent version, has 2 checks. Okay, now let me show you a sequence of figures very quickly. RAID 0 and 1, and I'll let you read the advantages and disadvantages for you. There are combination of zeros and 1, known as RAID 1.0. It uses both mirroring and striping. RAID 1E is a variant of RAID 1. Let me not go into the details. RAID level 2 uses coding. Used coding, it was abandoned pretty quickly. So for example, if you use Hamming 4.7 code, there are 4 data bits and 3 check bits. RAID 3 uses parity. RAID 4 also uses parity, but the parities are computed on larger blocks than in RAID 3. So it's somewhat more efficient. RAID 5 distributes the parity on different disks. So it doesn't use one disk for all the parities, and therefore it doesn't have the bottleneck for writes. RAID level 6 uses 2. So for example, blocks A0 and B0 have a parity block P0, have a parity block P0 and a second check Q0. And therefore 2 disk failures can be tolerated. Now one notion that I need to mention here is the notion of parity group. When you have, let's say, let me go back to RAID 5. If you have 4 disks and 1 spare, you really don't need to compute the parity across all the disks, all 4. You can define what is called a parity group. Imagine you have, this is particularly important when you have a large number of disks. Imagine you have 20 disks. You don't have to have your parity group equal to 20, where the parity is computed on 19 data blocks. You can have your parity group equal to 10, so that 9 data blocks and a parity block, and another 9 data blocks and another parity block. Making the parity group smaller has the advantage that when you're doing reconstruction, so if you have 20 disks and your parity group is 10, then 10 of the disks will be involved in reconstruction when something goes wrong. The other 10 disks will not be affected. They can continue operation at their full performance. And therefore, making the parity block smaller has this advantage. Of course, if the parity block is smaller, then the probability of failure goes up. So there's a trade-off. Okay, so I already talked about so this basically shows the effect of group size, parity group size, on performance for different RAIDs. So as you see, for example, RAID 3, as the group size increases, its performance deteriorates for small reads. So there are 4 categories. Small reads means reading of a small amount of information. Large reads means you're reading maybe thousands of bits, tens of thousands of bits, okay? Similarly for writes, small writes and large writes. Okay, large write performance increases with group size for RAID 3 and 5, and the smaller RAID for RAID 6, okay? So these are basically empirical studies that determine the performance. So for small reads and small writes, performance deteriorates as you increase the group size. For RAID 5, it deteriorates and then becomes stable after a while. Whereas for large writes and large reads, performance improves, throughput improves. So, there's a trade-off. If you make your block size too big, then you suffer here. If you make it too small, you suffer here. Okay, and finally, I show you these, without proof, these MTTF calculations for disk arrays. RAID 1, MTTF and MTTR are the numbers for a single disk. So if a single disk has MTTF, mean time to failure, MTTR, mean time to repair, then these formulas can be used to determine the MTTF. They're not hard to prove. For RAID 1, RAID 5, and RAID 6. These are the ones most commonly used nowadays. Okay, so you see that MTTF squared means if MTTF is large, this is a huge number. MTTR is typically a small number, so MTTF improves greatly. Here too, you have MTTF squared, but you also have G-1 in the denominator. So MTTF increase is not. So this 2 is because the n is equal to 2 there. Here you also have n, but also you have G-1. And then RAID 6, because it tolerates 2 errors, you have MTTF cube, MTTR squared. Okay, That's it for our discussion of error correction and error correcting code. And I'll see you in lecture 11. Stay safe until we meet again.